Thanks, Paolo, for the introduction. Actually, it's fun because we're both Italians, so it was the easiest setup ever done in Italian. So the bit link that you see under my Twitter handle, it's where you can find the source code, where you can find the slides of the presentation. It's already live, and if you want to download it, do it. Pony Drive, that's the code name of the project right now. You will understand why. So yeah, it's true. I am an engineering manager at Akamai Technologies. I'm the organizer of the droidCon Boston. That's more important for me. I'm also organizer of SwiftFest. Yes, I'm a strange beast. I do iOS and I do Android. I'm sorry. And I'm organizer also of other events. And I'm a founder of a meetup that is pretty popular in Boston and in Rome, where we mix music and technical talks. Today we're going to talk about computer vision, briefly, of course. We'll do the fastest ever introduction to OpenCV, and we'll discover how to set up OpenCV and Android SDK, and we'll start to detect traffic lights, detect driving lanes, and why not, detecting features from a video source, and understanding which are the challenges and next step of this pilot. The problem that we want to solve, it's pretty simple. Are common problems. We want to provide a better assistance solutions to everyone, a better driving experience to everyone. We want to be able to interpret correctly the signals, giving contextual information, and we want to reduce the number of accidents due to distractions. On the side, we would like to monitor how you drive and collect some information. So we want to understand if you are on the right lane. We want to understand if you are colliding something. And I want to understand these signals, because I cannot understand if I can park here or not, while we can process this image. The code name of this project is Pony Drive. So we want to actually prevent this, or facilitate this. It depends on the point of view. Computer vision. Computer vision, it's the way you combine magic into a software and you create illusions. That's one of the fantastic definition of OpenCV, of computer vision by Marco Tempes, and it's pretty interesting. The point of computer vision is that you start to work with different data sources, and every single image that comes into your device or into whatever device, it's a source of information. The tricky part is that you should create and have available good data sources. So you have to clean the information that are in the image, because every image, by default, it's a little bit dirty. An image, it's a two-dimensional projection of a 3D space. So actually, it's a quantized representation of the space, and it's usually defined by the function f of ij. What does it mean? It means that when you get something in a camera, you get this point that get obviously reverted from the camera, and then you have to start to deal with this two-dimensional representation that is on a plane of a 3D object. Let's start to have some common terminology. Images and frames are made up of pixels organized in a two-dimensional array. That's the most important information you have to keep in mind for all this presentation. In a color image, each pixel is represented by anything that is comprised between 8 and 32 bit. While a grayscale image uses only 8 bits per pixel. Why this is important? Because a gray image uses much less memory, and it's much more easy to be processed. So digital images are created by sampling a continuous image into discrete elements. And what happens is that every sensor consists of a two-dimensional array that is dealing with a three-dimensional space. So that's the magic that is happening through a camera. The number of samples in an image limits the object that can be distinguished, of course, because the more bits, the less bit you have, the less information you have. But a bit and a channel are very, very related to each other. Why? Because each pixel is a representation of the brightness of a given point, and typically the number of levels that are in every single channel are represented by k equal to elevated to the b. b, it's nothing more than the number of the bits, and often it's 8. Why this is important? It's important because the reduced number of bits, it's the key to process faster and effectively images on whatever device. At the end of the day, a colored image gives you a lot of information, but a grayscale image, it's not so bad. Color images are rich, have luminance and chrominance. At the end of the day, what is more important between the two, it's luminance. Why? Because if you take a look to this image, you can still recognize that this is a raster, correct? Well, the image in grayscale contains so much less information that you cannot imagine how this thing can impact the performance on any computer vision application. A grayscale image is smaller in size, is easier to analyze, and contains all information about the luminance. Of course, we don't have any chrominance information, and these information are enough to detect the edge of an image. When you have to deal with a grayscale image, your code is also smaller, cleaner, easier to understand, and, as I said several times, much more performing. Usually, when you deal with mobile devices, you want to get an image, and you want to start to process this image. I'm pretty sure that in this room we have all top-level devices, but that's not the truth for everyone. So in order to be effective with grayscale images, what you usually do, you reduce the size of the acquired image, usually at 25%. Then you determine the region of interest that you really want to get information, and you apply the grayscale transformation, and then you start to deal with the information, the two-dimensional array that OpenCV, in this specific example, give back to you. Every image contains noise. Noise, it's nothing more than a way to measure the degradation of an image. What does it mean? It means that the digital noise that it's in every single image can be mitigated through different techniques. One important thing to understand is that the digital noise is completely random, not predictable. So most of the techniques use random selection of pixels to mitigate the noise of the image. Image averaging, for instance, it's a technique that gives you, through random image, a better representation of the original image. You should be able to see that the column that is on the left, on the right, sorry, this one, is a little bit clearer than these other two. And these represent this square, another square that is here, and another square that is here. So this is a technique known as averaging. You are interested to the tail of the tree, the red square on the image, then what you do, it's you get this image and you pick additional images around this point, randomly, and then you average. You create an average of all of the images. There are other techniques, like the Gaussian filter or the salt and pepper filter. On these images, on these 4 images, we remove the digital noise by applying a filter that it's destroying a little bit the image, because a Gaussian filter, it's a little bit destroyer. But at the end of the day, we recognize better the objects. If you take a look to this gentleman, this version, it's much more clearer. But if you look at it carefully, here you understand better which are the objects, but here the details are more defined. So it's balanced. It depends what you have to do. Most of the time you have to recognize an object. You need less details, and a Gaussian filter or a salt and pepper filter help a lot to reduce the noise. Every image can be processed, and it depends, the way you are going to process an image depends on what you are searching for. In this sequence, for instance, we start from a colored image, and we land here. There are less details about the flowers, but in this example, I'm not interested into the flowers, but I'm interested to get more details about the person that is in this picture. So through image processing, in this case, variating the colors of every image, you can get a better and more clear representation of the image. These techniques are also known as thresholding. You can use thresholding techniques to separate the background from the foreground objects of your image. And you do this in order to really get what you are interested into. There are several algorithms that you can use with thresholding. One interesting thing about OpenCV, that is what I used to prepare this POC, this proof of concept, is that OpenCV keep hidden for you a lot of this complexity, simply exposing functions that do all the magic for you. Thresholding can be applied to get whatever you want. For instance, you can start from a grayscale image and you can get a binary image. So grayscale is not a black and white image. It's really grayscale. While a binary one, it's just black and white. Through thresholding, you can get the details that you need. Actually, in this image, you are not interested at all about the background, but just about the foreground, and you get a clearer representation of it through thresholding. One important thing when you deal with images is that you want to detect features. A feature in an image, it's something that you are interested into. It's a piece of information that you want to elaborate. Maybe an edge, maybe a light, maybe whatever that you're interested into. So there is not an exact definition about image features, because the definition depends on the problem and type of the application that you're trying to implement and the kind of problem that you're trying to solve. You can search for corners, you can search for blobs, you can be interested into edges, and so on. For instance, here we have two images. One on the left, it's the representation of the corner detection, and the one on the right, it's the representation of the blob detection. Are two features that you can get out from every single image. The description of a feature, it's the data that you get back. So once you got all your features, you start to process these features, and you start to understand what is in these features. You do this through feature descriptors. There are a lot of feature descriptors. All of them contain a sampling pattern, the orientation compensation, and the sampling pairs. You actually try to pair the feature that you detected with something else to understand if you recognize it correctly an object or not. The important thing is that there are several descriptors. The binary descriptors obviously contain much less information. The standard descriptor use floating point vectors, while a binary descriptor obviously use only 0 and 1s. These reduce the complexity, these reduce the time of processing, and so on. The brief descriptor describes an interest point with a set of pairs. The pairs are get randomically, and then you apply different randomization methods to get these random data. The orb feature descriptor add orientation to the brief. So actually you understand not just a feature, but also the orientation of the features. This can be very useful when you are trying to detect lights, source of lights, corners, and the pixel are get through the pixel are get through the variance and through the variance. Brisk, binary, robust, invariantable, scalable key points. You get 60 points, and you arrange this point in concentric rings. It's very similar to how the human retina works. And in fact, the Frick, that is the fast retina key point, use a circular shape and the same techniques of the BRISC. Let's take a look to the code. The code to get a descriptor is exactly this one. So here, I'm sorry, it's a little bit collapsed. We start to get a couple of arguments in a function that are the grayscale and RGB representation of an image, and we instantiate a feature detector. This feature detector creates a 50 points descriptor, and then we simply use and play with a for loop to draw circles on an image. Let's take a look to a demo. Maybe it's a little bit clearer. Here we go. Okay. So let's start to take a look to this feature descriptor. You see enough data on the screen. I'm detecting, in this case, I'm using not a binary descriptor. In fact, you see that it's a little bit slow in rendering every single feature. If we change to a binary one, you will get much more information, and if you see, it's a very faster, it's smoother, and you can detect whatever information. If I point at the light, I don't see lights. If I point at people, I can detect almost all the corners that are around Paolo, for instance. I can understand if it's sitting on a chair or not on a chair. This is basically what a feature descriptor does. That's interesting. Let's go back to where we were. We go. That's absolutely unexpected. I'm sorry about that. Give me a second to manually get where I was. Okay. Would be interesting without the title that are readable. But we'll see what we can do. Okay. You have to trust me about the title of every single slide. I'm sorry about that. Okay. We're almost back in business. So let's start to understand the building blocks of OpenCV. So in a nutshell, OpenCV is an image processing library. It's open source. It's available for C, C++, and Python. It's under the BSD open source license, so you can use it for whatever you want. Commercial uses are allowed, and it's not a problem. And it's easy to install and to use. Let's start to talk a little bit about the basic data structures of OpenCV. There is a point, there is the sides data structure, the rect, the rotated rect, and the mat object. The mat object, it's a matrix that represents the image. These are the data that you manipulate and you deal with to do any processing. The point object has a pretty simple constructor, several functions, including the inside one and the dot product of both of them. The sides, same thing, constructor as an area. The mat object, it's the most complex, has many, many items, because it can give you row and columns. It's a two-dimensional representation of the image. Can give you information about the channels that you are using in that image, and the depth. The OpenCV capabilities are pretty straightforward. Image and data manipulation. So you can allocate, copy, you can change settings, you can deal with video input and output, you can do basic image processing, and you can do motion analysis. On top of this, you can do object recognition. There are geometric transformation like resides, like wrap affine, like convert to maps. There are color transformation, like convert color, actually convert from a color space to another one. Threshold, it's a simple function, it's super powerful, give you all the possibilities that you can imagine. You can find connected components, and you can start to apply filters. So you can apply two-dimensional filters, box filters, Gaussian blur, and everything directly with these functions that belong to the namespace of OpenCV. Supported platforms. Windows. Trust me, that's Windows. Of course, Linux. It's not doing better results today than Windows. And Mac, Android, and iOS. So it's actually one of the few libraries that has pretty wide support of platforms. The design behind OpenCV, it's intended to be cross-platform. The library was written initially in C and then ported to C++. So now with OpenCV 3, well, actually since the version 2, but with OpenCV 3 we have an even better C++ interface for OpenCV. And right now almost all the algorithms are in C++. This makes the code a little bit more readable. Now you should be a little bit much more comfortable, because you know that all the complexity that we explored briefly about computer vision can be handled directly by OpenCV. Let's see how to set up OpenCV and the Android NDK together. In this way, we can take advantage of the OpenCV SDK for Android, that is a wrapper, a Java wrapper around the C++ function. So first of all, you download the last version of OpenCV. Then you take a look to what is inside of it. If you open the SDK folder, you'll see a Java folder and a native folder. The native one, it's very important because it's where you get all the compiled shared object, the compiled C++ shared object files. And the Java one, it's where the Android SDK actually resides. You start to create a new project, you include the C++ support, you import a new module pointing to the OpenCV Android SDK Java folder, and you accept the default options. At this point, you select the module and you specify that you want to compile it in your application. Once you have done this, be sure that the Gradle file that is contained in the OpenCV SDK and in your app match. What I mean is that the SDK that you want to compile for and you want to be compatible with have to be the same. Switch to the Android view, right-click, create a new folder, and you can create a JNI folder. The JNI folder, it's where you store all the C++ files. That's needed to extend a little bit the capabilities of OpenCV. You go back in OpenCV, and you also use the JNI folder to the JNI libs folder to store all the .so files that you find in the native folder that we saw before. Once you have done this, please comment this line in your Gradle file, the source set, because otherwise Android Studio, the last version, will not show you the JNI folders. It's important. I spent 2 hours to get there. Then you open the cmakelist.txt file, and you refer the lib OpenCV, that is the same name of the module that you have into your dependencies, in order to be sure that it's compiled. You add the static initialization of OpenCV, and you run the app. And that's it. But be very precise. Exactly this step. Let's take a quick look how to add existing libraries that you want to use with OpenCV. Why existing libraries? Because you can write less code, you can reuse code, and you can have cross-platform implementation. Plus, you improve the performances. The Java wrapper, it's fantastic, but it implies a single call for every function that you're going to call. If you store everything into a C++ file, you reduce the number of calls to the wrapper. You do exactly only one, and then you have everything available. So it's much faster. You open the project, you open the main activity, you search for a static native function that is created by default by Android Studio when you initialize the project, and then you create a new one. What does it mean? It means that you will have a new function into your native lib.c++ that has a terrible signature. It's something like this. Java, that's the package of your app, and so on. It's terrible, but it's what it's supposed to do by default. And then you refer to the new library. So if you take a look here, there is images lib C++, it's the new file that we created, and you refer this exactly here before the OpenCV one, because you have dependencies on OpenCV. You add another initializer, and here we go. You are ready to go. When you run the app, you will be able to get all the information that you need. The architecture of an Android app that want to use OpenCV stay almost the same. The only thing that you have to be careful is the JNI libs and the JNI folder. These have to be very well organized, because C++ is not like Java and neither like Kotlin. So you will get immediately a mess in your namespace. Executing directly C++, it's much, much more faster. The demo that you saw before, the features, are using directly C++. Now I will show you another demo where I am doing, I'm detecting the colors, and that's absolutely slower. Whoa. As you can see, I'm detecting the colors of the object on which I'm tapping. I'm tapping now on the white shirt that is in second line. I'm going now on the gray one that is on the back, and so on. This is slower. You see from the movement also of the camera. The why, it's pretty simple. I'm using the wrapper and not calling directly C++. It's so slower that you can take a look to this data. It's from Android Authority, this benchmark. So it's a 60% slower on Android 6. And then it depends on which kind of function you are executing. For instance, now the C++, if you don't use the, if you use the JNI wrapper, it's a little bit faster with Android 6 and the new 64-bit architecture. And again, here you are simply doing some other math operation, it's even faster. But all the other platforms, Android 4.4, 5, or 6 with a 32-bit architecture, it's 191% slower. So it's very important that you consider C++ seriously. But please, don't start to use only C++ and prototype fast with a wrapper and then start to move everything to C++. One important thing is about the dependency of OpenCV. OpenCV can be embedded in your application or can be managed through the OpenCV manager. The OpenCV manager, it's an app that stays on every store. It can be downloaded. You can force your app to download the manager, and the manager will do for you all the job. We'll download the latest version of OpenCV. We'll download and install automatically patches, bug fixing, and obviously it's shared at runtime, so it uses less memory, can be used between more applications, and it improves a lot the experience of the end user. That's the workflow. Usually, if there isn't, you install it, and if there is no OpenCV, it's the manager itself that is taking care of all the dependency for you. Let me show you. I think that it's better if we go with code. So first of all, I will show you what this other part of the demo is doing, if the app is not crashing again. There we go. So, now I'm applying an algorithm that it's pretty complex. It's the Kenny algorithm. As you can see, the image contains still a lot of details to understand, for instance, how many people there is in this room and that there are chairs. The Kenny algorithm, it's complex, but it's implemented in one single line of code in OpenCV. That's a binary representation of the same camera. And again, it's a little bit confused, but I'm getting... Now, better? But still contains a lot of information. On top of this, I'm detecting now the lanes, the straight lanes that are in this room. And I can detect also the lanes of this monitor or of this keyboard. So all these things really doesn't involve more than a few lines of code. So the binary detector, sorry, the view mode binary, the one that was pretty confusing, applied two different blur, same blurring, Gaussian blurs, and then make a difference between the first blurred image and the second blurred image. Once you have done this, you simply apply the threshold. It's better? More readable, right? Okay. And you apply the threshold, and everything got designed on the screen for you. When you want to deal with the Kenny algorithm, it's actually a single line of code. It's actually a single line of code because it's nothing more than apply the Kenny algorithm and convert the color. Same thing for the lines. Actually, the lines, it hide a little bit more complexity that it's stored into the lane detector and into the line equation that are here. But at the end of the day, are a bunch of for loop and a lot of information that you run into your application. Another thing, couple of things that I want to show you, we can use the simulator, is how to detect the traffic lights and how to detect the lanes of random street. Here we go. Whoa. Wrong device. Let's go with this. Should be fast enough. Yep. I don't want this. I don't care. Oh. The device was right. It's the app that is wrong. Here we go. That's good. 0 errors, 0 warnings. Waiting for the debugger. So, first of all, I want to show you the red circle that you see on the image, on the second image. That's to detect the point with the highest, strongest light in your image. This can be very helpful when you want to detect if the traffic light, because once you detect the source of the light, you can simply make an analysis of this part of the image. And detecting a color over there, it's absolutely trivial. And applying the half transform, you can start to detect the lanes that are in front of you. Before doing this, if you paid attention to the previous demo, the gray image, the black and white image, that's not any more than a Kenny algorithm that get applied to it. And you get back, you then apply enough transformation to get these lines. This is not, again, it's a lot of math behind the scene, but it's all this complexity, it's hidden. For you. It's hidden by, to you by OpenCV. And that's the math that you have to detect the edges. You simply convert from the RGB color space to the grayscale one, and that's line 62. Then you apply the Kenny algorithm, and actually that's it for the detection of the edges. The half transform has a little bit more complexity, but at the end of the day, you get all the lines through this function, through the half lines P that is directly from OpenCV. And then you do a for loop to draw something on the screen. And actually, you want to draw this something into the image that gets rendered on the screen. So you simply use the image processor object, and you say, please, draw a line that it's in the RGBA space that start, end, over there, and here you are controlling the color with the scalar. Okay. So to detect the light, we saw how to detect the light. The step to detect the lines, it's nothing more than this code that was rendered much better in Android Studio. And now I want to talk a few seconds about which are the other problems that we're trying to solve. So right now, Well, this obviously it's a demo. Thanks to God, it doesn't crash, at least not too much. The device camera can have different orientation in a car according to how you set up the camera. And that's a problem, because all these matte work with a very precise orientation and expecting that the camera is a good camera, that you get high-resolution images and so on. The orientation changed dramatically, whatever you are trying to do. There are unknown transformations that need to be applied to every single image accordingly to the external conditions. So you have to detect the external condition to understand if it's foggy, if it's raining, if it's snowing. You can imagine if it's snowing, what you can see on the screen when you detect the features, all the yellow dots. And there are cameras that varies. Every camera has different specification. You should change the algorithm accordingly to which are the specification of the camera, the characteristics, and you can optimize things accordingly to this data. Movement. Here, I'm getting images without moving. So I move the camera, but I'm not advancing. I'm not moving back and forward. That's a very important thing. The camera, given that it's never static, it's giving a lot of problems. So when we try whatever algorithm we used or we implemented in a car, things change dramatically. And we're trying to understand how we can mitigate this without asking to have the camera in a stable position. We need to mix a lot of data. For instance, one of the experimental thing that we're doing is interacting with Android Auto, and especially with the automotive hardware abstraction layer to get information about the car, speed, temperature, whatever that can give us much more information about the external data. Another thing that we are trying to do is to start to get to access to data set and train our algorithms against videos, against images, against other information that come from different data sources, and trying to mix everything together. So that's kind of it. There are questions. If everything is clear, it means that I did a terrible job because nobody understood anything, or that I said things that you already know. No questions? Are you sure? So I want to leave you with a quote. It's from the founder of Tesla. If you can count on having or not having an accident, you can get rid of a huge amount of the crash structure of the car and all the airbags, and this will save you money. That's one of the reasons why Tesla is investing so much on assisting driving solution. Thank you so much.